Artificial intelligence, often referred to as AI, is revolutionizing the way we interpret astronomical data, making it possible to analyze vast amounts of information that would otherwise be too daunting for human researchers alone. For instance, AI algorithms can sift through billions of data points collected from telescopes and space missions, identifying patterns and anomalies that might indicate the presence of new celestial bodies or phenomena. By using machine learning techniques, these systems can improve their accuracy over time, learning from previous data interpretations to enhance future analyses. This capability is particularly useful in the search for exoplanets, where AI can analyze light curves from stars to detect the subtle dimming caused by a planet passing in front of its host star, a method known as the transit method. Moreover, AI aids in classifying galaxies and other cosmic structures, which helps astronomers understand the evolution of the universe. Traditional methods of classification relied heavily on human observation and manual categorization, which were both time-consuming and prone to error. With AI, we can automate this process, allowing for more consistent and reliable classifications, and thus drawing more accurate conclusions about the universe's history and structure. Additionally, the use of AI in analyzing gravitational wave data has opened new avenues for understanding cosmic events such as black hole mergers, providing insights into the fundamental laws of physics. AI also plays a critical role in handling data from the numerous space missions currently in operation. For example, the James Webb Space Telescope, with its advanced capabilities, generates an immense amount of data daily. And AI helps in processing this data efficiently, ensuring that scientists can focus on the most promising findings. By employing natural language processing, AI can even assist researchers in literature reviews, summarizing relevant studies and highlighting key discoveries, which saves time and allows for more comprehensive research. Another fascinating application of AI in astronomy is in the realm of predictive modeling. By analyzing historical data, AI algorithms can predict potential future astronomical events, such as supernovae or asteroid impacts. This predictive power not only enhances our understanding of the universe, but also improves our preparedness for potential threats to Earth. Furthermore, AI can facilitate collaborative research across international teams, enabling scientists from different countries to share findings and insights, breaking down geographical barriers that have traditionally limited astronomical research. As AI technology continues to advance, its role in interpreting astronomical data will only grow, potentially leading to discoveries that could change our understanding of the cosmos. With ongoing developments in AI, the future looks promising, as we may soon uncover new galaxies, understand dark matter. Astronomical data refers to the information that scientists gather from observing celestial objects, such as stars, planets, galaxies, and other astronomical phenomena. This data is crucial for understanding the universe and our place within it. In astronomy, there are several types of data that researchers commonly collect, each providing unique insights into the workings of the cosmos. One of the primary types of astronomical data is photometric data, which involves measuring the intensity of light from celestial objects. This type of data helps astronomers determine the brightness, color, and distance of stars, and can also reveal important information about the composition and size of these objects. Spectroscopic data is another key category, as it involves analyzing the light spectrum emitted or absorbed by astronomical objects. Through spectroscopy, astronomers can identify the chemical elements present in stars and galaxies, as well as their temperature, density, and velocity. This data is essential for understanding stellar processes and the evolution of galaxies. Additionally, astrometric data, which involves precise measurements of the positions and movements of celestial bodies, allows scientists to track the orbits of planets and stars, and is crucial for calculating distances in space. This information can help confirm the existence of exoplanets or planets outside of our solar system. Radio data is also significant, as it involves capturing radio waves emitted by astronomical sources, such as pulsars and quasars. This type of data has led to groundbreaking discoveries, including insights into the behavior of black holes and the structure of the universe itself. Moreover, the advent of modern telescopes and space observatories has allowed for the collection of vast amounts of data across different wavelengths, including infrared and ultraviolet light. This multi-wavelength approach provides a more comprehensive view of astronomical phenomena, allowing scientists to piece together a more complete picture of the universe. In recent years, advancements in technology have enabled the use of large-scale surveys, which collect and analyze data from millions of celestial objects, providing invaluable statistics for studying cosmic evolution and the distribution of matter in the universe. Furthermore, data from gravitational waves, ripples in space-time caused by cataclysmic events like black hole mergers, has opened a new window into understanding the universe, as it provides information that is not accessible through traditional electromagnetic observations. As astronomers continue to refine their techniques and equipment, the types of astronomical data being collected will likely expand, leading to new discoveries and a deeper understanding of the vast cosmos that surrounds us, with each type of data offering a unique perspective. Over the last decade, the volume of astronomical data has experienced an explosive increase, driven by rapid advancements in technology, which have transformed how we observe, collect, and analyze information from the cosmos. Telescopes, both ground-based and space-based, have become increasingly sophisticated, allowing astronomers to capture more detailed images and spectra from distant celestial objects. For instance, the introduction of large survey telescopes, such as the Pan-STARRS and the upcoming Vera C. Rubin Observatory, has significantly increased our ability to map the night sky, capturing millions of images and generating terabytes of data, which can be analyzed to study everything from asteroids to supernovae. Moreover, advancements in sensor technologies such as charge-coupled devices, CCDs, and infrared detectors have enhanced the sensitivity and resolution of astronomical instruments, enabling scientists to detect fainter objects that were previously beyond reach. This has led to discoveries of numerous exoplanets, as well as a better understanding of the early universe, where light from the first galaxies is just beginning to reach us. In addition, the rise of radio astronomy, with facilities like the Square Kilometre Array, promises to generate even more data, as it will observe the universe in unprecedented detail across a wide range of frequencies. Computational power has also played a crucial role in managing the growing data. High-performance computing allows astronomers to process and analyze vast data sets, employing complex algorithms and machine learning techniques, which can identify patterns and anomalies in the data that humans might miss. For example, the use of AI in analyzing data from gravitational wave detectors, such as LIGO, has led to rapid advancements in our understanding of black hole mergers and neutron star collisions, showcasing how technology can enhance our interpretation of astronomical phenomena. Furthermore, data sharing and collaboration among scientists has become more prevalent thanks to the internet and open source platforms, which facilitate the distribution of data from major projects like the Hubble Space Telescope and the Gaia mission, which is mapping the Milky Way with extraordinary precision. This interconnectedness allows researchers around the globe to contribute to a collective understanding of the universe as they analyze the same data sets, leading to new insights and discoveries. As we look to the future, the advent of next-generation space telescopes, such as the James Webb Space Telescope, is set to further revolutionize the field, with its ability to observe the universe in infrared wavelengths, opening up previously hidden regions of space. With each technological leap, the volume of astronomical astronomers, while delving into the vastness of space, encounter numerous challenges when it comes to analyzing large data sets, which can be both complex and daunting. One of the primary issues is the sheer volume of data that modern telescopes and observatories generate, with instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope capturing images and information at unprecedented resolutions. This flood of data requires sophisticated storage solutions and fast processing capabilities, as managing terabytes or even petabytes of information can overwhelm traditional computing systems. Moreover, astronomers must develop new algorithms and software tools to sift through this data efficiently, identifying patterns and anomalies that may indicate new celestial phenomena or provide insights into the universe's working. Another significant challenge is the noise present in astronomical data, which can obscure the signals that scientists are trying to analyze. This noise can arise from various sources, including the instruments themselves, atmospheric conditions, and even light pollution from urban areas. Therefore, astronomers must employ advanced techniques such as machine learning and statistical analysis to distinguish between the true signals of celestial objects and the background noise, all while minimizing the risk of false positives, which can lead to incorrect conclusions about astronomical events. Additionally, the complexity of the data itself poses another hurdle. Astronomers often deal with multi-dimensional data sets, meaning they need to analyze not just images, but also time series data, spectroscopic data, and other forms of information that are interrelated in intricate ways. This multidimensionality requires a deep understanding of both the data and the physical principles underlying the observed phenomena, as well as the ability to integrate different types of data into a cohesive analysis. Collaboration is also essential in this field, as many large data sets are generated by international projects that involve teams of scientists from various disciplines. Coordinating efforts across different institutions and ensuring that everyone is using compatible methods can be challenging, especially when researchers have differing levels of expertise with the tools and techniques needed to analyze the data effectively. This means that astronomers must not only be skilled in their own research areas, but also be flexible and willing to learn from their colleagues while sharing knowledge and best practices. Lastly, there's the issue of interpreting the results, which can be just as challenging as obtaining the data itself. Once the analysis is complete, astronomers must communicate their findings in a way that is understandable to both the scientific community and the general public. This requires not only a strong grasp of the science involved, but also the ability to convey complex ideas in the realm of astronomy. Machine learning has emerged as a powerful tool distinct from traditional data analysis methods, which have been used for decades to interpret the vast amounts of data generated by telescopes and other astronomical instruments. Traditional methods, often based on statistical techniques, rely heavily on predefined models and assumptions about the underlying data. These approaches typically involve fitting particular mathematical functions to the data, allowing astronomers to extract meaningful information such as the characteristics of celestial objects, their movements, or the structure of galaxies. However, these methods can be limited by the reliance on prior knowledge and can struggle with the complexity and scale of modern astronomical data sets. In contrast, machine learning, which is a subset of artificial intelligence, leverages algorithms that can learn from data, identifying patterns and making predictions without being explicitly programmed to do so. This capability is particularly advantageous in astronomy, where the sheer volume of data stemming from sources like large surveys or simulations can be overwhelming. Machine learning models, such as neural networks, can process and analyze vast data sets much more swiftly and often more accurately than traditional methods. They can detect subtle patterns in the data that might be missed by conventional techniques, revealing new insights into the universe. For instance, consider the area of galaxy classification. Traditional approaches might categorize galaxies based on their shapes or brightness, but machine learning can analyze multiple features simultaneously, such as color, texture, and light curves, to classify them into categories with greater precision. Additionally, machine learning can handle noisy data, which is common in astronomical observations, by learning to distinguish between signal and noise, thus improving the reliability of the results. Moreover, machine Learning excels in anomaly detection, a crucial aspect of astronomy, where researchers seek to identify unusual or rare events, such as supernovae or gravitational waves, among the vast quantities of normal data. Traditional techniques might require extensive manual inspection or predefined criteria, while machine learning algorithms can autonomously learn what constitutes an anomaly, resulting in faster discoveries and the potential to uncover phenomena that were previously overlooked. Another significant difference is the adaptability of machine learning models. Once trained on a data set, these models can be fine-tuned or retrained with new data, allowing astronomers to refine their analysis as new observations are made. This adaptability contrasts sharply with traditional data analysis methods, which often require a complete overhaul of the analytical framework to incorporate new findings or changes in understanding. Furthermore, the integration of machine learning in astronomy fosters collaboration across disciplines. As experts in computer science, data artificial intelligence plays a crucial role in pre-processing astronomical data, transforming the way scientists analyze vast amounts of information gathered from the cosmos. In the realm of astronomy, data comes from various sources, such as telescopes, satellites, and space probes, generating enormous volumes of images, spectroscopic data, and time series data, which can be incredibly complex and challenging to interpret. Here, AI algorithms, particularly machine learning techniques, are employed to automate the initial stages of data processing, which significantly reduces the workload of astronomers and enhances the efficiency of research. One of the primary applications of AI in this field is in the classification of astronomical objects. For instance, deep learning models, which are a subset of machine learning, can be trained on large data sets of labeled images to recognize different types of celestial bodies, such as stars, galaxies, and supernovae. By using convolutional neural networks, researchers can achieve high accuracy in identifying these objects, even in the presence of noise or artifacts that often occur in astronomical images. This capability allows scientists to quickly sift through thousands of images, pinpointing relevant targets for further study, rather than manually examining each one. Another significant role of AI in pre-processing is in the area of data cleaning and calibration. Astronomical data often contains errors due to various factors, including atmospheric interference, instrumental noise, and other environmental conditions. AI algorithms can analyze these data sets to identify and correct anomalies, ensuring that the data is accurate and reliable. For example, unsupervised learning techniques can be used to identify outliers or inconsistencies in the data, which can then be flagged for further investigation or removed altogether, leading to cleaner data sets that yield more trustworthy results. Moreover, AI assists in the extraction of features from complex data sets, enabling astronomers to derive meaningful insights from raw data. Through techniques like feature engineering, AI can help identify key characteristics of astronomical phenomena that may not be immediately obvious. For instance, algorithms can analyze light curves from variable stars, extracting patterns that indicate changes in brightness, which can provide valuable information about the underlying physical processes at play. In addition to these pre-processing tasks, AI is instrumental in automating the discovery of new astronomical phenomena. By applying techniques like anomaly detection, machine learning models can scan through large data sets to spot unusual patterns that may indicate the presence of previously unknown celestial events, such as transiting exoplanets or gravitational waves. This capability not only accelerates the pace of discovery, but also helps to ensure that potentially significant findings do not go unnoticed. AI algorithms have become essential tools in improving the accuracy of astronomical observations, as they are capable of processing vast amounts of data, which is often beyond human capabilities. One significant way they contribute is through image analysis. Telescopes, including powerful space-based observatories like Hubble, capture images of distant galaxies, stars, and other celestial bodies, generating terabytes of data every single night. AI can quickly analyze these images, identifying patterns and anomalies that may indicate the presence of a new celestial object or event, such as a supernova, which might go unnoticed by human eyes, overwhelmed by the sheer volume of data. Moreover, machine learning algorithms can enhance image quality by reducing noise, which is often caused by atmospheric interference or limitations in the instruments themselves. By training on existing high-quality images, these algorithms learn to distinguish between genuine astronomical signals and random noise, allowing them to create clearer, more accurate images from less than perfect data. This capability is particularly valuable in areas like exoplanet detection, where the signature of a planet transiting in front of a star can be incredibly faint, requiring precise measurements to confirm its existence. Additionally, AI plays a crucial role in automating and accelerating the process of data classification. Astronomers often need to categorize various types of celestial phenomena, from different kinds of stars to galaxies of varying shapes and sizes. Traditional methods can be time-consuming and prone to human error, but AI can quickly classify these objects based on learned features from previous data sets, improving both the speed and accuracy of classifications. For example, the Galaxy Zoo project has utilized crowdsourcing and AI to classify millions of galaxies, enabling a more efficient approach to understanding the universe's structure. AI algorithms also assist in predicting astronomical events. By analyzing historical data, these algorithms can identify trends and patterns that help astronomers anticipate future occurrences, such as meteor showers or the behavior of variable stars. This predictive power enhances our understanding of celestial mechanics and can lead to exciting discoveries about the dynamics of the universe. Furthermore, AI aids in the optimization of telescope operations. With the help of AI, telescopes can be programmed to select the most interesting targets to observe based on real-time data analysis. This adaptability ensures that valuable observation time is used effectively, focusing on phenomena that are most likely to yield significant scientific insights. Finally, AI's ability to simulate astronomical phenomena reinforces its role in improving observational accuracy. Scientists can create virtual models of celestial events, such as galaxy collisions or star formation, allowing them to compare these simulations. Artificial intelligence, or AI, has made significant strides in various fields, and astronomy is no exception. One of the most exciting ways AI can assist in the identification of celestial objects and images is through its ability to analyze vast amounts of data much faster than a human could. Traditional methods of identifying celestial objects often involve painstakingly examining images taken by telescopes, which can be time-consuming and labor-intensive. However, AI algorithms, particularly those based on machine learning, can be trained to recognize patterns in images, allowing them to identify stars, galaxies, asteroids, and other celestial bodies with remarkable accuracy. For example, deep learning models, which are a subset of machine learning, can process images by breaking them down into pixels and analyzing these pixels to detect features that correspond to different types of celestial objects. By training on thousands or even millions of labeled images, these models learn to differentiate between various objects based on their shapes, colors, and brightness. This training enables AI to not only identify known celestial objects, but also to discover new ones, as it can detect anomalies or unusual patterns that may indicate previously unobserved phenomena. Another way AI assists in the identification process is through the use of image classification techniques. These techniques allow AI to categorize objects within a celestial image into predefined classes, such as stars, planets, and nebulae. This classification can greatly enhance the efficiency of astronomical surveys, as researchers can quickly sort through images, focusing their attention on promising candidates for further study. For instance, the European Space Agency's Gaia mission uses AI to process vast amounts of data, helping astronomers map the positions of over 1 billion stars in our galaxy. Moreover, AI can also help in the identification of transient celestial events, such as supernovae or gamma-ray bursts. These events are often brief and can be challenging to spot amidst the noise of background objects. By employing AI algorithms that are specifically designed to detect changes over time, astronomers can analyze sequences of images to identify these fleeting events more effectively. This capability not only improves the chances of observing rare events, but also enhances our understanding of their properties and the underlying physics. Furthermore, AI can assist in improving image quality through techniques such as image enhancement and noise reduction. Telescopes often capture images that are affected by atmospheric conditions or instrumental noise, which can obscure faint celestial objects. AI-based algorithms can be used to enhance these images, making it easier to identify and study celestial objects that might otherwise be lost in the noise. In the realm of astronomy, convolutional neural networks, or CNNs, have become a powerful tool for classifying images, enabling scientists to analyze vast amounts of data collected from telescopes and satellites in ways that were previously unimaginable. CNNs are a type of deep learning model specifically designed to process grid-like data, such as images, by mimicking the way human brains recognize patterns. When applied to astronomical images, CNNs can identify and classify celestial objects like stars, galaxies, and nebulae with remarkable accuracy. The process begins with the collection of images often taken from different wavelengths, such as visible light, infrared, or radio waves. These images are then fed into the CNN, which consists of multiple layers, each designed to extract different features from the images. The initial layers might detect simple patterns like edges or textures, while deeper layers can recognize more complex structures, such as the spiral arms of galaxies or the glowing gas clouds of star-forming regions. One significant advantage of using CNNs in astronomy is their ability to handle large data sets. Telescopes like the Hubble Space Telescope or upcoming projects such as the James Webb Space Telescope generate enormous volumes of data, far too much for human astronomers to analyze manually. CNNs can process these images quickly and efficiently, making it possible to classify thousands of objects in a matter of hours or even minutes. This capability is crucial, especially in the era of big data, where researchers are continually seeking to extract meaningful information from their observations. Moreover, CNNs can improve classification accuracy by learning from labeled data sets. Scientists can train these networks using images that have already been classified, allowing the model to learn the characteristics of different celestial objects. This training process involves adjusting the network's parameters so it becomes better at recognizing patterns and distinguishing between different types of objects. For instance, when classifying galaxies, the network can learn to differentiate between elliptical galaxies, which appear smooth and featureless, and spiral galaxies, which have distinct arms and structures. In addition to improving classification speed and accuracy, CNNs can also uncover new insights in astronomical research. By analyzing previously unclassified or poorly understood objects, CNNs can help identify anomalies or rare phenomena, potentially leading to new discoveries. For instance, researchers have used CNNs to classify transient events like supernovae or gamma-ray bursts, which are critical for understanding the life cycles of stars and the dynamics of the universe. Furthermore, the application in the vast, mysterious realm of astronomy, anomaly detection holds a crucial role, as it allows scientists to identify unusual patterns or data points in celestial data sets, which in turn can lead to groundbreaking discoveries. The universe is filled with countless stars, galaxies, and other celestial phenomena, producing an overwhelming amount of data that can be challenging to analyze. Anomalies, such as unexpected bursts of light from distant stars, unusual movements of celestial bodies, or even the presence of unknown cosmic structures, can provide valuable insights into the workings of the universe. For example, a sudden increase in brightness from a star might indicate a supernova, while an unexpected trajectory of an asteroid could suggest it is being influenced by an unknown force. Detecting these anomalies is not merely about identifying outliers. It's about recognizing potential new phenomena that could change our understanding of astrophysics, cosmology, and the very fabric of space-time. This is where artificial intelligence, or AI, steps in as a powerful tool to enhance our capabilities in anomaly detection. Traditional methods of data analysis often rely on predefined models and can miss subtle anomalies due to their rigid frameworks. AI, particularly machine learning algorithms, can analyze vast data sets without such constraints, learning from the data itself to identify patterns that might be too complex for human analysts to discern. For instance, AI can sift through millions of light curves from variable stars, identifying those that behave unexpectedly, thus flagging potential supernovae or other transient phenomena for further investigation. This kind of analysis not only speeds up the detection process, but also increases the accuracy of identifying true anomalies from random noise, which is a common challenge in astronomical datasets. Moreover, AI can adapt and improve over time, learning from new data and refining its anomaly detection capabilities. By employing deep learning techniques, researchers can create models that recognize intricate features in the data, such as the subtle shifts in light intensity that might indicate the presence of an exoplanet transiting in front of its star. As new astronomical surveys generate data at an unprecedented rate, traditional methods may struggle to keep up. But AI can continuously learn and adapt, ensuring that no significant anomaly goes unnoticed. Additionally, anomaly detection using AI can foster collaboration across various fields of science, as the techniques developed for astronomy can be applied to other domains, such as biology and climate science, where recognizing outliers can lead to significant breakthroughs. The benefits of employing AI in anomaly detection extend beyond just speed and accuracy. They also encourage a more exploratory approach to data analysis. Natural language processing, or NLP, is a fascinating field that combines computer science and linguistics, and it has become increasingly useful in various areas of research, including astronomy. In astronomical research literature, NLP can be applied in several impactful ways, enabling researchers to sift through vast amounts of data and extract meaningful information more efficiently than ever before. One significant application is in the analysis of research papers and scholarly articles. There are millions of published papers in astronomy, and manually reading them all can be a daunting task, even for the most dedicated scientists. With NLP techniques, researchers can automate the extraction of key information, such as findings, methodologies, and even references. This means that instead of spending countless hours searching through articles for specific topics, scientists can use software tools that leverage NLP to summarize relevant content, identify trends, and highlight important discoveries. Another exciting way NLP is applied in astronomy is through sentiment analysis, which can help assess the overall tone of research publications. By analyzing the language used in papers, researchers can gauge whether the community's sentiment towards specific theories or discoveries is positive, negative, or neutral. This can provide insights into how certain ideas are received and whether there is growing support for new hypotheses or a pushback against established theories. Furthermore, NLP can assist in organizing and categorizing research literature, allowing for better information retrieval. By using algorithms to classify documents based on their content, researchers can easily find literature relevant to their specific interests, making the process of staying updated with recent advancements far more manageable. Additionally, NLP can enhance collaboration within the astronomical community by analyzing communication patterns in research discussions, such as those taking place in online forums or social media. Scientists can identify key contributors and emerging ideas, fostering a more interconnected scientific community. NLP techniques can also help in translating research findings into more accessible language, making complex astronomical concepts easier to understand for the general public, educators, and even policymakers. This democratizes scientific knowledge, ensuring that more people can engage with and appreciate the wonders of the universe. Moreover, the integration of NLP with machine learning can lead to the development of predictive models that forecast future research trends based on existing literature and citation patterns. By understanding how certain topics evolve over time, astronomers can better prepare for upcoming challenges and opportunities in their fields. In the realm of data analysis, NLP can also facilitate the processing of observational data, such as interpreting the notes made by astronomers during observations, or analyzing citizen science contributions by converting unstructured text data into structured formats. Artificial intelligence, or AI, has become a powerful tool in the field of astronomy, particularly in the discovery of exoplanets, which are planets located outside our solar system. One of the most significant applications of AI in this area is the analysis of data from space telescopes, such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite known as TESS. These telescopes collect vast amounts of data, and AI algorithms, particularly machine learning methods, help scientists sift through this information to identify potential exoplanets. For example, researchers have developed neural networks that can analyze light curves, which are graphs that show the brightness of stars over time, to detect the subtle dips in brightness that occur when a planet transits or passes in front of its host star. This method has proven to be much more efficient than traditional techniques, allowing astronomers to discover new exoplanets at a much quicker pace. Moreover, AI is also utilized in the classification of exoplanets, enabling scientists to distinguish between different types, such as gas giants, rocky planets, and super-Earths. By training algorithms with existing data, AI can learn to recognize patterns and features that characterize various exoplanet types, which helps researchers in understanding their formation and evolution. In addition, AI systems can analyze the atmospheric composition of these distant worlds by interpreting data from spectroscopic observations, revealing important information about potential habitability. Another fascinating application of AI in exoplanet discovery is in the field of citizen science. Platforms like Planet Hunters allow amateur astronomers and the general public to participate in the search for exoplanets by classifying light curves and identifying transiting candidates, with AI assisting in the process to enhance accuracy, thereby making the discovery of exoplanets a collaborative effort that spans beyond professional astronomers. AI can also help predict which stars are most likely to host planets, guiding telescopes to focus on the most promising targets, thus optimizing the search process. Furthermore, advancements in AI technology, such as reinforcement learning, have opened new avenues for exploration. This approach allows algorithms to learn from their successes and failures, enabling them to refine their methods in real time, which can be especially useful in identifying exoplanets in complex data sets. For instance, recent studies have utilized AI to enhance the precision of measuring the mass and radius of exoplanets, providing deeper insights into their physical properties. In summary, the integration of AI into the discovery of exoplanets has transformed artificial intelligence, or AI, is revolutionizing many fields, and one of the most exciting applications is in the analysis of gravitational wave data. Gravitational waves, which are ripples in space-time caused by some of the universe's most violent events, like merging black holes or neutron stars, carry vital information about these cosmic occurrences. However, the data generated by gravitational wave detectors such as LIGO and Virgo is immense and complex, making it challenging for scientists to sift through it all efficiently. This is where AI comes in, offering powerful tools to enhance our understanding of the universe. AI algorithms, particularly those related to machine learning, can be trained to recognize patterns in the vast amounts of data produced by gravitational wave observations. By analyzing previous events and their corresponding waveforms, AI can learn to identify potential signals from new data, distinguishing them from noise. This pattern recognition capability can significantly reduce the time it takes to find and confirm gravitational wave events, allowing researchers to focus their efforts on more detailed studies of these phenomena. Moreover, AI can assist in the classification of gravitational wave sources. Different astrophysical events produce unique waveforms, and by using AI, scientists can categorize these events more accurately. For instance, whether the waves originate from binary black hole mergers, neutron star collisions, or other celestial phenomena, AI can help identify the source type more quickly and with greater precision than traditional methods. Another exciting use of AI is in data cleaning and preprocessing. The raw data collected by gravitational wave detectors is often contaminated with noise from various sources, including seismic activity, human-made vibrations, and even cosmic rays. AI can be employed to filter out this noise, enhancing the quality of the data before it undergoes further analysis. By automating this process, researchers can ensure that the signals they analyze are as clean and accurate as possible, leading to more reliable results. Furthermore, AI can help in the simulation of gravitational wave signals. By generating synthetic data that mimics real gravitational wave events, AI can assist scientists in training their models and improving their detection algorithms. This not only helps in refining the tools used for analysis, but also provides a better understanding of what to expect from future observations. AI's ability to handle and analyze big data sets efficiently also opens new avenues for collaboration among researchers. With cloud computing and AI-driven analysis tools, scientists from around the world can share their findings and insights more readily. This collaborative approach can lead to a more comprehensive understanding of gravitational waves and the events that produce them. Artificial intelligence, or AI, has become a powerful tool in the field of astronomy, especially when it comes to identifying transient astronomical events, which are those fleeting phenomena that occur in the universe, such as supernovae, gamma-ray bursts, and variable stars. One of the primary ways AI assists in this area is through its ability to process vast amounts of data quickly and accurately. For decades, astronomers have been collecting data from telescopes, both ground-based and space-based, generating an overwhelming volume of information that can be difficult to sift through manually. AI algorithms, particularly machine learning models, can analyze this data effectively, identifying patterns and anomalies that might indicate the presence of transient events. Moreover, AI can help improve the speed at which these events are detected. Traditional methods of analyzing astronomical data rely heavily on human observation, which can be time-consuming and prone to oversight. In contrast, AI systems can continuously monitor the sky, scanning images and light curves for sudden changes that signify a transient event. For instance, when a new supernova occurs, it can brighten dramatically over a matter of days, and AI can be trained to recognize these rapid changes, alerting astronomers in real time. Another intriguing application is in the field of classification. Once a transient event is detected, AI can assist in categorizing it based on its characteristics. By training on existing data sets of known transients, AI models can learn to differentiate between various types of events, such as distinguishing between a type Ia supernova and a type II supernova, which have different origins and implications for our understanding of the universe. This a classification process, which would take human astronomers much longer to accomplish, can be done in a fraction of the time with AI, allowing researchers to focus their efforts on the most interesting or significant discoveries. Additionally, AI can enhance the predictive capabilities of astronomers. By analyzing historical data and current observations, AI algorithms can help predict when and where transient events might occur in the future. This predictive power can guide observatories in their observing schedules, ensuring that they are looking at the right parts of the sky at the right times, maximizing the chances of catching a fleeting event. Furthermore, AI can assist in the interpretation of complex data from multi-wavelength observations. Transient events can be studied across various parts of the electromagnetic spectrum, including radio, optical, and X-ray wavelengths. AI algorithms can integrate and analyze these different data sets, providing a more comprehensive understanding of the event and its implications. Artificial intelligence, or AI, has become an invaluable tool in the field of astronomy, especially when it comes to classifying galaxies based on their morphology, which refers to their shape and structure. Traditionally, astronomers would painstakingly analyze images of galaxies, categorizing them into different types, like spiral, elliptical, or irregular. This process was time-consuming and often subjective, relying heavily on the experience and judgment of the astronomer. However, with the advent of AI, particularly machine learning algorithms, this classification process has become much more efficient and accurate. AI algorithms can be trained on vast data sets of galaxy images, using deep learning techniques to recognize patterns and features that distinguish different morphological types. For instance, researchers feed thousands or even millions of labeled images into the AI system, allowing it to learn the characteristics of each galaxy type. As the AI processes these images, it identifies subtle differences in shape, brightness, and structure that may not be immediately obvious to the human eye, enhancing the accuracy of the classification. Moreover, AI can analyze images from various telescopes, including ground-based observatories and space telescopes like the Hubble Space Telescope. This ability to handle diverse data sets allows AI to provide classifications that are consistent across different observational conditions, which is crucial for large-scale astronomical surveys that gather data from multiple sources. An exciting development in this area is the use of convolutional neural networks, or CNNs, which are particularly effective for image analysis. These networks can examine the pixel-level details of galaxy images and automatically extract features relevant to their classification. For instance, a CNN might learn to recognize the spiral arms of a galaxy or the smooth, rounded shape of an elliptical galaxy, enabling it to classify new images with remarkable speed and precision. Additionally, AI tools can help astronomers discover new types of galaxies that may not fit neatly into existing categories. By clustering galaxies with similar features, AI can reveal unexpected morphological diversity, prompting astronomers to rethink how galaxies are classified. This has significant implications for our understanding of galaxy formation and evolution, as it allows researchers to explore the vast array of structures that exist in the universe. Importantly, while AI enhances classification accuracy, it also acts as a collaborative partner for astronomers. Human experts can review and refine the AI's classifications, ensuring that the final results are both scientifically sound and insightful. This synergy between AI and human expertise leads to a more comprehensive understanding of galaxies, revealing the intricate tapestry of structures that populate our universe. The ethical considerations surrounding the use of artificial intelligence in astronomy are multifaceted and complex, as they touch upon various aspects of research, data handling, and the broader implications of technology in scientific discovery. One significant concern is the potential for bias in the algorithms that are used to analyze astronomical data. If the data used to train these AI systems is not comprehensive or is skewed in some way, it could lead to inaccurate conclusions about celestial phenomena. For instance, if an AI model is trained predominantly on data from certain types of stars or galaxies, it may overlook or misinterpret data from others, which can skew our understanding of the universe. Moreover, there is the issue of transparency and accountability in AI decision-making processes. In astronomy, where discoveries can lead to significant advancements in our understanding of the cosmos, it is crucial that the methodologies employed by AI systems are clear and understandable to researchers. If astronomers cannot fully comprehend how an AI arrived at a particular conclusion, it may lead to mistrust in the findings and hinder progress in the field. This becomes even more critical when considering the collaborative nature of astronomical research, as findings often rely on the contributions of many scientists across different institutions and countries. Another important ethical consideration is data privacy and the ownership of data. As telescopes and observational technologies become more advanced, they collect vast amounts of data from the night sky. This data may include not only information about astronomical objects, but also sensitive data regarding the locations of observatories or even private property. Ensuring that this data is handled responsibly while respecting the rights of individuals and institutions is essential. There's also the question of intellectual property. Who owns the discoveries made by AI? Should it be the researchers who develop the AI, the institutions funding the research, or the community at large? Furthermore, the use of AI in astronomy raises questions about the future role of human astronomers. As AI systems become more capable of identifying patterns and making predictions, there is concern that the role of astronomers may shift significantly. Will we still need human intuition and creativity in the discovery process, or will AI take over many of these functions? This leads to broader discussions about the relationship between humans and technology and how we can ensure that AI serves as a tool to enhance human understanding rather than replacing the unique cognitive abilities that humans bring to scientific inquiry. Lastly, there is the potential for AI to inadvertently contribute to environmental issues, especially when considering the energy consumption associated with training large AI models. Astronomy often relies on artificial intelligence, or AI, is revolutionizing many fields. And one significant area where it can enhance efficiency, particularly in large-scale surveys like the Legacy Survey of Space and Time, or LSST, is in data processing. The LSST, designed to capture vast amounts of astronomical data, will generate petabytes of information, which can be overwhelming for traditional data processing methods. AI can step in to streamline this process, making it faster and more accurate. For instance, machine learning algorithms can be trained to recognize patterns in the data, assisting in the identification of celestial objects, such as stars, galaxies, and transient events like supernovae. By automating the classification process, AI can significantly reduce the time astronomers spend sorting through data manually, allowing them to focus on analysis and interpretation. Furthermore, AI can help in anomaly detection, which is crucial for identifying unusual or unexpected phenomena in the sky. For example, by using neural networks, scientists can train models to flag data that deviates from the norm, which could indicate a new discovery or a rare event. This capability not only speeds up the identification process, but also increases the likelihood of catching fleeting cosmic events that might otherwise be missed. Another way AI enhances efficiency is through predictive analytics. By analyzing historical data, AI can help forecast where and when certain astronomical events are likely to occur, guiding observational strategies and optimizing the survey's scheduling. In addition, natural language processing, a branch of AI, can assist researchers by parsing through vast amounts of scientific literature and data repositories, extracting relevant information and summarizing findings, which can save time and provide insights that may not be immediately obvious. Moreover, AI can improve data quality through automated error correction and validation processes, ensuring that the data analyzed is as accurate as possible, which is essential in scientific research. By integrating AI into the data processing pipeline of the LSST, researchers can achieve a higher level of efficiency, enabling them to handle the immense data load more effectively and leading to more discoveries about our universe. As this technology continues to advance, its role in data processing will likely become even more critical, opening new frontiers in our understanding of the cosmos. Artificial intelligence, or AI, plays a fascinating and increasingly significant role in the simulation of cosmic events like supernovae and black hole collisions. As scientists strive to understand the complex and often chaotic nature of these astronomical phenomena, AI offers powerful tools that enhance our ability to model, analyze, and predict outcomes. In simulations of supernovae, for instance, AI algorithms can process vast amounts of data from telescopes and previous observations, identifying patterns that may not be immediately apparent to human researchers. By employing machine learning techniques, AI can help refine models of how stars explode, allowing scientists to simulate various scenarios based on different initial conditions, such as the mass of the star or its composition. Moreover, in the realm of black hole collisions, AI is utilized to analyze gravitational wave data collected from detectors like LIGO. When two black holes merge, they create ripples in space-time, which can be detected on Earth. AI algorithms are trained to sift through the noise in this data, identifying potential signals of black hole mergers more efficiently than traditional methods. This capability not only speeds up the detection process, but also helps in classifying the events and estimating the properties of the black holes involved, such as their masses and spins. Additionally, AI can simulate the behavior of matter under extreme conditions, such as those found near black holes or during supernovae. By using advanced computational models, AI can help researchers understand how different types of matter behave in these environments, leading to insights about the fundamental laws of physics. This is particularly important because the conditions in these cosmic events are so extreme that traditional physics might not fully apply, and AI can assist in exploring these unknowns. Furthermore, AI can contribute to visualizing these cosmic events, creating stunning simulations that not only help scientists but also engage the public's imagination. By transforming complex data into visual formats, AI allows us to witness the spectacular beauty of supernovae explosions and the dramatic collisions of black holes, making the science more accessible and inspiring. As technology advances, the integration of AI in astrophysics will likely continue to evolve, leading to new discoveries about our universe while enhancing our understanding of both the cosmos and the fundamental forces at play. Reinforcement learning, a type of machine learning, is emerging as a powerful tool in the field of astronomy, especially when it comes to optimizing observational strategies. In traditional observational astronomy, scientists often rely on predefined schedules and fixed strategies for collecting data, which may not always yield the most valuable insights. However, by integrating reinforcement learning algorithms, astronomers can create adaptive systems that learn from past observations, improving the efficiency and effectiveness of their data gathering efforts. For instance, these algorithms can analyze vast amounts of previous observational data, identifying patterns and relationships that humans might miss. By simulating different observational scenarios, reinforcement learning can predict which celestial events are most likely to provide significant information, allowing astronomers to focus their resources more effectively. This means that instead of randomly selecting which stars or galaxies to observe, a reinforcement learning model can suggest the best targets based on their potential to yield new discoveries. Furthermore, reinforcement learning can adapt to real-time conditions. For example, if a telescope encounters unexpected weather changes, the algorithm can quickly adjust the observational schedule, prioritizing targets that are observable under the current conditions, while also considering the scientific value of those observations. This dynamic adjustment is crucial as it maximizes the utility of telescopes and other observational instruments, especially when they are limited in time and resources. In addition to optimizing telescope time, reinforcement learning can also enhance survey strategies for large-scale projects such as sky surveys that aim to map the entire night sky. By continuously learning from incoming data, these systems can modify their approach, targeting areas of the sky that show unusual activity or phenomena like transient events such as supernovae or gamma-ray bursts. This not only saves time and effort, but also increases the chances of capturing rare astronomical events that could lead to groundbreaking discoveries. Moreover, the applications of reinforcement learning extend to data analysis as well. After observations are made, the data collected can be incredibly complex and massive in size. Reinforcement learning algorithms can help streamline the data processing phase, learning to identify and categorize celestial objects more efficiently than traditional methods. This capability allows astronomers to sift through enormous data sets rapidly, identifying interesting targets for further study. As we delve deeper into the cosmos, the role of artificial intelligence, particularly reinforcement learning, will become increasingly vital. It will allow astronomers to not only maximize the efficiency of their observational strategies, but also to push the boundaries of what we know about our universe, making the exploration of the cosmos more dynamic and fruitful than ever before. The implications of AI-driven discoveries for our understanding of the universe are vast, and they touch on many areas of science and exploration, opening doors to new ways of thinking about our cosmos. Artificial intelligence, with its powerful algorithms and vast data processing capabilities, is revolutionizing how we analyze astronomical data, enabling us to uncover patterns and phenomena that were previously hidden from human observation. For instance, in the search for exoplanets, AI has been instrumental in analyzing the light from distant stars, detecting the subtle dimming that indicates a planet passing in front of them, a method known as the transit method. This technology allows scientists to sift through enormous data sets from telescopes like the Kepler Space Telescope, identifying potential planets with remarkable speed and accuracy, which not only increases our count of known exoplanets, but also helps us understand their characteristics and potential habitability. Moreover, AI is enhancing our ability to simulate cosmic events, such as supernovae or the formation of galaxies, providing insights into their underlying physics. By employing machine learning techniques, researchers can create sophisticated models that predict how these events unfold, allowing us to explore scenarios that would be difficult to replicate through traditional means. This computational power also aids in the analysis of gravitational waves, where AI algorithms can comb through the noise of data collected from detectors like LIGO, identifying signals from distant black hole mergers, which in turn informs us about the nature of gravity and the structure of the universe. Furthermore, AI is assisting in the quest to understand dark matter and dark energy, which together constitute about 95% of the universe's total mass energy content, yet remain largely mysterious. By analyzing large-scale structures in the universe, AI can help uncover how these elusive components influence the formation and evolution of galaxies, providing a clearer picture of the universe's history and fate. The ability of AI to process and analyze data from various sources, including telescopes, satellites, and cosmic simulations, means that our understanding of the universe is becoming more interconnected, revealing relationships and insights that may have been overlooked. In the realm of cosmology, AI is also being utilized to analyze cosmic microwave background radiation, the afterglow of the Big Bang, helping scientists refine models of the early universe and understand its expansion. This analysis sheds light on fundamental questions about the origins of the universe, its rate of expansion, and the potential for multiverse theories, which propose the existence of multiple, perhaps infinite universes, each with its own laws of physics. AI, artificial intelligence, or AI, is revolutionizing the way we analyze data from space telescopes, enhancing both the reliability and the efficiency of the information we gather about the universe. Space telescopes, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, collect an enormous amount of data, capturing images and spectra across various wavelengths to study distant galaxies, stars, and other celestial phenomena. However, the sheer volume of this data can make it challenging for scientists to process and extract meaningful insights, leading to the potential for human error and oversight. This is where AI comes into play, providing innovative solutions to improve data reliability. One significant way AI enhances data reliability is through advanced image processing techniques. Machine learning algorithms can be trained to identify and correct artifacts in telescope images such as noise and distortion caused by atmospheric interference or instrument limitations. By effectively cleaning up these images, AI not only improves the quality of the data, but also ensures that the scientific conclusions drawn from these images are based on clearer, more accurate representations of celestial objects. This has been particularly useful in the study of exoplanets, where precise measurements are crucial for determining the atmospheres and potential habitability of these distant worlds. Additionally, AI can assist in the classification of celestial objects, an area traditionally reliant on human interpretation. By utilizing deep learning models that analyze vast data sets, AI can quickly categorize stars, galaxies, and other astronomical phenomena with high accuracy. This not only saves time, but also reduces the potential for human bias in classification, leading to more reliable data. For instance, researchers have successfully employed AI to identify new types of supernovae, which might have been overlooked in manual reviews, thus enriching our understanding of cosmic events. Moreover, AI helps in anomaly detection, which is crucial in space observation. When telescopes collect data, it's essential to discern between regular patterns and unusual occurrences. AI algorithms can learn from historical data sets to recognize what constitutes a typical signal from a star or galaxy, allowing them to flag anomalies that warrant further investigation. This capability is vital for identifying new phenomena, such as fast radio bursts or gravitational waves, which could provide insights into the fundamental workings of the universe. In addition to image processing and classification, AI can optimize observational strategies for space telescopes. By predicting the best times to observe certain celestial objects based on their movements and brightness, AI can help astronomers allocate telescope time more effectively. This optimization not only maximizes the scientific output from each observation session, but also ensures that the AI technologies have made significant strides in processing and analyzing vast amounts of astronomical data, yet there are still notable limitations that researchers and scientists face. Although AI can identify patterns, recognize anomalies, and assist in classifying celestial objects, it often struggles with understanding the complex context behind the data it analyzes. For example, while AI can detect exoplanets through transit methods, it may not fully grasp the astrophysical implications of those findings, such as the planet's atmosphere or potential for habitability, which requires a deeper understanding of physics and chemistry that AI lacks. Furthermore, astronomical data is often noisy and incomplete, which can lead AI algorithms to make incorrect assumptions or predictions, as they may misinterpret the random fluctuations in the data as meaningful signals. Moreover, AI models are typically trained on existing data sets, which can introduce biases if the data is not comprehensive or diverse enough, leading to gaps in knowledge about certain celestial phenomena or types of objects. Additionally, the interpretability of AI decisions remains a challenge. When an AI system makes a discovery or classification, it can be difficult for scientists to understand why the AI reached that conclusion, which limits the trust and reliance on these systems in scientific research. Furthermore, the sheer volume of astronomical data produced, especially from initiatives like the Large Synoptic Survey Telescope, can overwhelm current AI capabilities, necessitating ongoing advancements in both hardware and algorithms to keep pace with the influx of information. Also, collaboration between AI technologies and human experts is crucial, as humans bring intuition and contextual understanding that AI currently cannot replicate, highlighting the need for a complementary approach rather than a replacement. While AI shows promise in revolutionizing how we interpret astronomical data, its limitations remind us of the importance of human insight and expertise, especially in a field as vast and intricate as astronomy. Integrating AI into existing astronomical research workflows can enhance our understanding of the universe in profound ways, as it allows researchers to analyze vast amounts of data more efficiently, pinpointing patterns and anomalies that would take humans much longer to detect. For instance, AI algorithms can be employed to sift through data collected from telescopes, identifying celestial objects such as stars, galaxies, and exoplanets much faster than traditional methods. By utilizing machine learning techniques, astronomers can train algorithms to recognize specific features in the data, which helps in classifying different types of celestial phenomena, and this in turn can lead to new discoveries, as AI can even suggest hypotheses that researchers may not have considered. Moreover, AI can assist in processing images captured by powerful telescopes like the Hubble Space Telescope or the upcoming James Webb Space Telescope. These telescopes produce enormous amounts of data, and AI can help in cleaning up images, removing noise, and enhancing details, making it easier for scientists to visualize and analyze distant galaxies or nebulae. Another exciting application is in the realm of gravitational wave detection, where AI can analyze signals from detectors like LIGO, distinguishing between actual gravitational waves and background noise, which can be a challenging task for traditional analysis methods. Additionally, AI can play a critical role in automating the repetitive tasks that often bog down researchers, such as calibrating data or conducting initial analyses. This automation frees up valuable time for astronomers, allowing them to focus on more complex questions and innovative research. Furthermore, AI can contribute to predictive modeling, helping researchers to simulate cosmic events or the behavior of celestial bodies under various conditions, leading to a deeper understanding of phenomena such as black holes or supernovae. Collaborative platforms that utilize AI can also enhance the sharing of knowledge among astronomers, creating a network where findings can be disseminated quickly and efficiently, thus accelerating the pace of discovery. By integrating AI into existing workflows, researchers can also gain insights from interdisciplinary fields, as AI techniques developed in areas like biology or computer science can be adapted and applied to astronomical challenges, leading to innovative solutions. Moreover, there's a growing emphasis on citizen science projects, where AI can help engage the public in astronomical research by analyzing data from amateur astronomers. This not only broadens the scope of research, but also fosters a sense of community and shared discovery among enthusiasts worldwide. With AI continually evolving, its integration into astronomical research workflows promises to transform how we explore and understand the cosmos, making it an understood citizen. Science plays a vital role in the intersection of artificial intelligence and astronomical data interpretation, providing a bridge between the vast amounts of data generated by modern telescopes and the insights that can be gleaned from that data. With the advancement of technology, telescopes now capture an incredible volume of information, from images of distant galaxies to the faint signals of exoplanets, and this data can be overwhelmingly complex. Here, citizen scientists or everyday individuals who contribute to scientific research come into play, bringing fresh perspectives and enthusiasm to the field. By participating in various projects, they help analyze and interpret astronomical data, allowing professional astronomers to focus on more complex analyses, while also providing valuable insights that might otherwise be overlooked. One notable example is the use of citizen science platforms like Zooniverse, where volunteers can classify images of stars, galaxies, and other celestial objects. With the help of AI, these platforms can streamline the process using machine learning algorithms to sort through data and flag interesting features that citizens can then investigate further. This collaboration between AI and citizen scientists not only accelerates data processing, but also enhances the quality of the analysis by incorporating human intuition and creativity, which can sometimes spot patterns or anomalies that machines might miss. Moreover, citizen science in astronomy fosters community engagement and education, allowing participants to learn about the universe while contributing to actual research. Many projects are designed to be user-friendly, encouraging people from various backgrounds to participate, regardless of their previous knowledge of astronomy. For instance, participants might help identify and categorize types of galaxies, track the movement of asteroids, or even search for new planets outside our solar system. This democratization of scientific research empowers individuals, making them active contributors to our understanding of the cosmos. Additionally, as AI continues to evolve, the relationship between citizen science and data interpretation in astronomy will likely deepen. AI systems can analyze trends in citizen-contributed data, providing insights into how collective human input can complement machine learning. The synergy between AI and citizen science not only enhances data interpretation, but also broadens participation in scientific research, allowing more people to connect with the wonders of the universe. In essence, citizen science serves as a crucial component in the realm of AI and astronomical data interpretation, transforming ordinary individuals into key players in the quest to unravel the mysteries of the cosmos. By leveraging the power of technology, the unique perspectives of citizen scientists, and the analytical capabilities of AI, we can deepen our understanding of the universe while fostering a sense of connection, and AI can play a transformative role in automating the classification of stellar spectra, which are crucial for understanding the properties of stars, such as their temperature, composition, and age. Traditionally, classifying these spectra has required significant expertise and manual effort, as astronomers analyze the light emitted from stars, seeking to identify various features and patterns such as absorption lines, which indicate the presence of different elements. With the advent of AI, particularly machine learning techniques, this process can be made much more efficient. For instance, AI algorithms can be trained on large data sets of previously classified stellar spectra, allowing them to learn the distinguishing characteristics associated with different spectral types. By using deep learning techniques, particularly convolutional neural networks, AI can analyze spectra images, identifying subtle features and patterns that may be missed by human eyes. This capability not only speeds up the classification process, but also enhances accuracy, as AI can process vast amounts of data without fatigue, consistently applying the same criteria across multiple spectra. Moreover, AI can help in categorizing spectra into more complex classifications, such as distinguishing between different subtypes of stars within the same spectral class. This is particularly useful in large astronomical surveys, where millions of spectra may need to be classified quickly. For example, projects like the Sloan Digital Sky Survey have generated extensive data sets, making them ideal candidates for AI applications. AI can also adapt to new data, refining its models as more information becomes available, which is essential in astronomy, where new discoveries frequently challenge existing classifications. In addition to classification, AI can assist in identifying unusual or rare objects within stellar spectra, such as peculiar stars or new types of celestial phenomena. By flagging these anomalies, AI can direct astronomers' attention to objects that may warrant further study, potentially leading to groundbreaking discoveries. Furthermore, the use of AI in this context helps democratize access to astronomical data, as even those with limited experience in spectroscopy can utilize AI tools to gain insights and make classifications. As the field of astronomy continues to evolve, the integration of AI technologies will likely result in a deeper understanding of the universe, allowing for quicker, more accurate analysis of stellar spectra, which can ultimately contribute to our knowledge of star formation, evolution, and the overall dynamics of galaxies. With ongoing advancements in AI, the future of stellar classification looks promising, heralding a new era of exploration and discovery in the cosmos. Artificial intelligence, often referred to as AI, has been revolutionizing various fields. And one area where its impact is particularly noteworthy is in the collaboration between astronomers and data scientists. In the realm of astronomy, vast amounts of data are generated from telescopes and space missions, which can be overwhelming for scientists to analyze manually. This is where AI comes into play, providing powerful tools that can process and interpret complex data sets at incredible speeds. For instance, machine learning algorithms can identify patterns in the data that might be too subtle or intricate for human observers, such as the faint signatures of distant galaxies or the slight variations in light from exoplanets. Moreover, AI enhances the efficiency of collaborative projects. Astronomers who often have a deep understanding of the universe and its phenomena can partner with data scientists who possess the technical expertise in coding and algorithm design. Together, they can create innovative models that not only speed up data processing, but also improve the accuracy of their findings. For example, in the search for gravitational waves, AI analyzes signals from detectors like LIGO, helping researchers pinpoint events that require further investigation. The collaboration also extends to the realm of simulation and modeling. AI can help simulate cosmic events such as supernova explosions or galaxy formations, allowing astronomers to test their hypotheses in a virtual environment before applying them to real-world observations. Through this synergy, both fields benefit. Astronomers gain insight from data science techniques, while data scientists can apply their skills to address scientific challenges, leading to groundbreaking discoveries. Furthermore, AI is instrumental in automating routine tasks, which frees up valuable time for researchers to focus on more complex problems. Consider the process of classifying astronomical objects. Traditionally, this would require countless hours of manual work. However, with the help of AI, classification can be done in a fraction of the time, resulting in a more comprehensive understanding of the cosmos. Additionally, AI facilitates global collaboration, with the internet enabling researchers from different parts of the world to share data and findings. AI tools can help integrate diverse data sets, making it easier to conduct large-scale studies that were previously unfeasible. This is crucial, especially in projects like the Sloan Digital Sky Survey, where data from various telescopes is combined to create a detailed map of the universe. In conclusion, the impact of AI on the collaboration between astronomers and data scientists is profound and multifaceted. It not only streamlines data analysis and enhances the accuracy of scientific research, but also fosters innovation through interdisciplinary transfer learning. Is a fascinating concept in the field of artificial intelligence, especially when we look at its application in astronomy, which is a domain filled with vast amounts of data and complex patterns. Essentially, transfer learning allows models trained on one task to be adapted for another, often related task, which can be incredibly beneficial in fields like astronomy, where labeled data can be scarce. For instance, when researchers develop AI models to identify celestial objects, they often begin their training on data sets that are rich and well annotated, such as images from other domains like natural scenes, or even synthetic data generated based on physical laws. By using what the model has learned from these initial data sets, astronomers can fine-tune the AI system to recognize features in astronomical images, such as galaxies, stars, or exoplanets, with greater accuracy. This process not only speeds up the training of the AI models, but also enhances their performance, allowing them to make predictions or classifications on astronomical data that they haven't explicitly trained on. For example, if a model learns to recognize the general features of a galaxy from a vast data set of labeled images, it can then be applied to new, unlabeled astronomical images, significantly reducing the time and effort required for human astronomers to classify and analyze these images. Furthermore, transfer learning can help in situations where there is a need to adapt to new types of data as they become available, such as data from new telescopes or different wavelengths of light, which may not have been part of the original training set. Astronomy has some of the most challenging data analysis problems, with images that can vary widely in quality, resolution, and the types of objects present. Transfer learning helps overcome some of these challenges by allowing astronomers to leverage existing models that have already learned valuable features from different but related data sets. This is particularly useful in areas like detecting gravitational waves, identifying exoplanets via transit photometry, or classifying supernovae, where the nuances of the data can be subtle and complex. By utilizing transfer learning, astronomers can focus their efforts on interpreting the results and making discoveries rather than getting bogged down in the labor-intensive process of data labeling and model training from scratch. Moreover, as new astronomical surveys and instruments come online, the ability to quickly adapt existing AI models through transfer learning means that the scientific community can keep pace with the growing influx of data. This adaptability is crucial as the universe is constantly unveiling new phenomena, and having the tools to analyze this data efficiently. Artificial intelligence, or AI, has made remarkable strides in the field of astronomy, revolutionizing how researchers analyze vast amounts of cosmic data. One notable case study is the work conducted by the European Space Agency, specifically with the Gaia mission. Launched in 2013, Gaia aims to create a detailed three-dimensional map of our galaxy, the Milky Way. With its ability to capture billions of star positions and movements, the mission generates an overwhelming amount of data. AI algorithms, particularly machine learning, have been employed to process this data, identifying stellar patterns and categorizing stars based on their properties, which would have been nearly impossible for humans to achieve manually. In another instance, AI has been used to identify exoplanets, those fascinating worlds orbiting stars outside our solar system. The Kepler Space Telescope, which operated from 2009 to 2018, collected data on thousands of stars, revealing potential exoplanets. Researchers developed AI models to analyze light curves from these stars, distinguishing between regular stellar activity and signals indicating the presence of planets. This approach significantly increased the efficiency of exoplanet detection, leading to the identification of numerous new candidates for further study. Additionally, the use of AI in gravitational wave astronomy has transformed our understanding of cosmic events. The LIGO Laser Interferometer Gravitational Wave Observatory project, which detects ripples in space-time caused by massive astronomical events like black hole mergers, generates immense amounts of data. AI techniques, particularly neural networks, have been instrumental in filtering out noise from the signals, allowing scientists to focus on genuine gravitational wave events. This application of AI has not only enhanced detection capabilities, but also accelerated the analysis process, leading to quicker discoveries and a deeper understanding of the universe. Moreover, the Hubble Space Telescope has benefited from AI through image processing techniques. Researchers have utilized deep learning algorithms to enhance the quality of images captured by Hubble, allowing for clearer views of distant galaxies, nebulae, and other celestial phenomena. By training AI to recognize and correct common image artifacts, astronomers can produce more accurate representations of the universe, facilitating better analysis and interpretation of cosmic structures. Lastly, the ongoing development of the Square Kilometer Array, a radio telescope project expected to be one of the largest and most advanced in the world, is heavily reliant on AI. The sheer volume of data generated from the numerous radio signals collected will require sophisticated AI systems to process and interpret the information. This initiative aims to explore AI can be a powerful tool in predicting future astronomical phenomena. And this is mainly achieved through the analysis of vast amounts of historical data, which includes information from telescopes, satellites, and other observational tools. By using machine learning algorithms, AI systems can identify patterns in the historical data, recognizing trends and relationships that may not be immediately obvious to human researchers. For instance, AI can sift through millions of data points collected from various celestial events like supernovae, comet appearances, or variable stars, and detect subtle signals that indicate the likelihood of similar events occurring in the future. One fascinating application is in the prediction of asteroid trajectories. Historically, astronomers have tracked these celestial bodies using mathematical models, but with the integration of AI, researchers can enhance the accuracy of their predictions. Machine learning algorithms trained on past asteroid data can analyze factors such as gravitational influences, orbital mechanics, and other celestial interactions, leading to better forecasts of an asteroid's path and potential close approaches to Earth. This predictive capability is crucial for planetary defense, as it helps scientists assess the risk of potential impacts. Moreover, AI can also be applied to the study of exoplanets. which are planets outside our solar system. By examining light curves from distant stars, researchers can detect transits where a planet passes in front of its star, causing a slight dimming. AI can automate the processing of this data, identifying potential exoplanets more efficiently than traditional methods. Additionally, it can help predict characteristics of these planets, such as their size, composition, and distance from their stars, which are vital for understanding their habitability. In the realm of cosmic events, AI has shown promise in predicting phenomena like gamma-ray bursts, which are extremely energetic explosions observed in distant galaxies. By analyzing historical data on these bursts, AI can help researchers identify patterns and triggers, leading to better predictions of when and where they might occur again. This information is not only fascinating for astronomers, but also essential for understanding the evolution of the universe. Furthermore, AI can assist in studying the cosmic microwave background, which is the afterglow radiation from the Big Bang. By using deep learning techniques, researchers can analyze the data collected from satellites like the Planck Observatory, allowing for more accurate measurements of cosmic parameters, such as the rate of expansion of the universe. These insights can lead to new theories about the universe's fate. As telescopes and observatories continue to gather unprecedented amounts of data, the role of AI in astronomy, relying too heavily on artificial intelligence in astronomical research, presents several potential risks that merit careful consideration. Firstly, one major concern is that AI systems, while powerful, can sometimes lack the ability to understand context, which is crucial in the complex field of astronomy. For example, an AI might misinterpret data from a distant galaxy simply because it doesn't grasp the nuances of astronomical phenomena, leading to incorrect conclusions that could misguide future research. Additionally, AI models are often trained on existing data, which means they may not account for new or unexpected discoveries, creating a risk of bias in research outcomes. If researchers become too dependent on AI, they might overlook vital anomalies or new patterns that don't fit established algorithms, ultimately stifling innovation and discovery. Moreover, the black box nature of many AI systems can pose significant challenges, particularly in terms of transparency. Scientists must be able to understand and explain their findings. However, if an AI system generates results without clear reasoning, it becomes difficult to validate those conclusions. This lack of transparency can hinder peer review processes and complicate collaboration among researchers. Furthermore, there is a risk that reliance on AI could lead to a reduction in traditional observational skills among astronomers. If researchers increasingly defer to AI for data analysis, they may become less adept at interpreting raw data themselves, potentially weakening their analytical capabilities over time. Another critical issue involves the ethical implications of AI in astronomical research. The use of AI technologies raises questions about data ownership, privacy, and the potential for misuse of information. If AI systems are trained on sensitive or proprietary astronomical data, the risk of data breaches or exploitation increases. Additionally, there is the possibility of unequal access to AI tools, where only well-funded institutions can afford advanced AI technologies, creating disparities in research opportunities and outcomes across different organizations. Finally, the dynamic nature of astronomical phenomena means that reliance on AI could lead to stagnation in research methodologies. As astronomers depend on AI to process data, there may be less incentive to develop new theories or explore unconventional ideas that could lead to groundbreaking discoveries. In summary, while AI has the potential to revolutionize astronomical research, it is essential to approach its integration thoughtfully, ensuring that the scientific process remains robust, diverse, and open to new ideas. Artificial intelligence, or AI, has become an invaluable tool in many fields of science, including astrophysics, particularly in the quest to understand dark matter and dark energy, which together make up about 95% of the universe's total mass energy content, yet remain largely mysterious. One way AI assists in this search is through the analysis of vast amounts of data collected from telescopes and observatories. For instance, projects like the Large Synoptic Survey Telescope, which will capture images of the night sky, generate petabytes of data, and AI algorithms can sift through this data quickly, identifying patterns, and anomalies that may indicate the presence of dark matter or dark energy. These algorithms can learn from previous data, improving their accuracy over time, and can also help in classifying galaxies and detecting gravitational lensing, a phenomenon caused by the bending of light around massive objects, which is a key indicator of dark matter. Moreover, AI can enhance simulations of cosmic structures, helping scientists understand how dark matter influences the formation and behavior of galaxies. By using machine learning, researchers can create models that predict how galaxies should behave under different dark matter scenarios, which can then be tested against actual observations, allowing for a more nuanced understanding of the universe's composition. Additionally, AI can assist in optimizing the design of experiments and observations, ensuring that telescopes and detectors are used effectively, focusing on the most promising targets for identifying dark matter and dark energy signatures. In the realm of particle physics, AI plays a critical role in analyzing results from particle colliders like the Large Hadron Collider, where researchers search for particles that might be associated with dark matter, such as WIMPs or axions. By training machine learning models on previous collision data, scientists can improve their search strategies, enhancing their chances of detecting rare events that could provide clues about these elusive components of the universe. Furthermore, AI helps in automating the review of research papers and preprints, allowing scientists to stay updated with the latest findings and hypotheses regarding dark matter and dark energy, thereby fostering collaboration and innovation in the field. AI also assists in citizen science projects where amateur astronomers and the general public can contribute to the search for dark matter by classifying galaxies or identifying unusual celestial phenomena, augmenting the efforts of professional scientists. The combination of human insight and AI's processing power can lead to breakthroughs that single approaches might miss. Ultimately, the intersection of AI with astrophysics represents a fascinating frontier, one where technology and human curiosity jointly push the boundaries of our artificial intelligence, or AI, has become a crucial tool in the field of astronomy, particularly in enhancing the capabilities of radio telescopes. These enormous instruments, which collect radio waves from space, rely on advanced technology to interpret the vast amounts of data they gather. AI plays several key roles in this process, beginning with data analysis, where machine learning algorithms are utilized to sift through the enormous data sets generated by radio observations. Traditional methods of data analysis can be time-consuming and often struggle to identify patterns or anomalies in the data. However, AI algorithms, which can learn from large data sets, are exceptionally good at recognizing patterns, enabling scientists to detect new celestial objects, such as pulsars or quasars, with greater accuracy and speed. Moreover, AI enhances the imaging capabilities of radio telescopes. Radio astronomy often involves creating images from radio signals, a process known as imaging or synthesis. AI techniques, particularly deep learning, have been applied to improve the quality of these images, allowing for clearer and more detailed representations of astronomical phenomena. By training AI models on previously known images, researchers RS can fine-tune these algorithms to reconstruct images with less noise and more detail, which is critical for studying distant galaxies or cosmic events like supernovae. In addition to improving image quality and data analysis, AI also assists in the calibration of radio telescopes. Calibration, which ensures that the collected data accurately reflects the source signals, is a complex and essential task in radio astronomy. AI can automate parts of this process, making it more efficient and less prone to human error. By analyzing the data in real time, AI can help astronomers adjust their equipment dynamically, optimizing observations as conditions change. AI also aids in the optimization of telescope operations. For instance, predictive algorithms can forecast when celestial events like meteor showers or eclipses are likely to occur, allowing telescopes to be pointed at the right place at the right time. This capability maximizes the efficiency of observations, ensuring that astronomers are capturing valuable data when it matters most. Furthermore, AI can help manage the scheduling of multiple telescopes, coordinating their observations to create a more comprehensive picture of the universe. Another fascinating aspect of AI in radio astronomy is its role in citizen science projects. By using AI algorithms to analyze data, researchers can engage the public in identifying celestial phenomena, allowing amateur astronomers to contribute to scientific discoveries. This collaboration not only expands the reach of radio astronomy, but also fosters a greater appreciation for our universe among the general public. Furthermore, AI, artificial intelligence, or AI, is making significant strides in various fields, including astrophysics. And one of its remarkable applications is in the analysis of cosmic microwave background radiation data. The cosmic microwave background, often referred to as CMB, is the afterglow of the Big Bang, providing a snapshot of the universe when it was just about 380,000 years old. This faint radiation fills the universe and carries with it a wealth of information about the early stages of cosmic evolution, the formation of structures in the universe, and the fundamental parameters of cosmology, such as the curvature of space and the density of different types of matter. AI techniques, particularly machine learning, are being employed to sift through the vast amounts of data collected by observatories like the Planck satellite, which has been mapping the CMB with unprecedented precision. The challenge lies in the complexity and sheer volume of the data, which can contain noise and other contaminants that obscure the underlying signals we wish to study. Traditional methods of data analysis can be time-consuming and may not always yield the most accurate results, which is where AI comes in. By utilizing machine learning algorithms, researchers can train models to recognize patterns in the CMB data. For instance, convolutional neural networks, a type of deep learning model, can be trained on simulated CMB maps to identify features such as temperature fluctuations and polarization patterns that point to the presence of gravitational waves or the influence of dark energy. These algorithms can learn to differentiate between the signals we want to analyze and the noise that can interfere with our understanding of the CMB. Moreover, AI can enhance the efficiency of data processing. For example, unsupervised learning techniques can cluster similar data points, helping scientists to identify anomalies or unexpected results that could lead to new discoveries. This means that rather than manually analyzing every data point, researchers can use AI to focus on the most promising areas of data, accelerating the pace of scientific inquiry. Additionally, AI can assist in creating simulations of the early universe based on the CMB data. By employing generative models, researchers can simulate various cosmological scenarios and see how they would manifest in CMB observations. This can lead to better theoretical models of the universe's evolution, helping to refine our understanding of phenomena such as inflation, the rapid expansion of the universe shortly after the Big Bang, and the distribution of galaxies we observe today. Furthermore, AI can help in the task of cross-correlating CMB data with other astronomical observations. By linking, in recent years, the field of astronomy has witnessed a remarkable transformation, largely driven by the interdisciplinary applications of artificial intelligence, or AI, which has begun to intersect with various other scientific fields, enhancing our understanding of the cosmos in profound ways. One exciting area is the integration of AI with physics, particularly in the analysis of gravitational waves. By applying machine learning algorithms to the data collected from observatories like LIGO, scientists can identify and classify waveforms, allowing for a deeper understanding of cosmic events such as black hole mergers or neutron star collisions, phenomena that were once elusive to direct observation. In addition to physics, AI is proving invaluable in the realm of biology, especially in astrobiology, where researchers use AI to analyze data from missions searching for signs of life on other planets. For example, AI algorithms can sift through vast amounts of spectral data from telescopes, identifying potential biosignatures on exoplanets by detecting specific chemical signatures that indicate the presence of life-sustaining conditions, thus bridging the gap between biology and astronomy. Furthermore, the integration of AI with computer science is paving the way for advancements in data processing and simulation techniques, enabling astronomers to model complex cosmic phenomena more accurately. This collaboration allows for the creation of simulations that predict the formation of galaxies or the behavior of dark matter, providing insights that were previously unattainable due to computational limitations. Moreover, AI's application in environmental science is also noteworthy, particularly in the study of space weather and its effects on Earth's atmosphere. By using AI to analyze data from satellites and ground-based observatories, scientists can better predict solar flares and their potential impact on satellite communication or power grids, demonstrating how astronomy can intersect with environmental science to safeguard technology and infrastructure on Earth. In the field of chemistry, AI plays a crucial role in analyzing the chemical composition of celestial bodies. For instance, by examining the light spectra emitted by stars and planets, AI algorithms can help determine the elemental makeup of these bodies, providing insights into their formation and evolution, which in turn informs our understanding of the universe's chemical diversity. Additionally, AI is being utilized in archaeology, particularly in the study of ancient astronomical sites. By employing machine learning techniques to analyze satellite images, researchers can uncover previously unknown structures or alignments that reveal how ancient civilizations interacted with the cosmos, showcasing the cultural significance of astronomy throughout human history. AI is also making strides in the field of mathematics, particularly in solving complex problems related to celestial mechanics and orbital dynamics. By utilizing advanced artificial intelligence, or AI, is making waves in many fields, and astronomy is no exception with its ability to process vast amounts of data. AI can significantly contribute to the development of new astronomical instruments. For instance, machine learning algorithms can analyze data from telescopes much faster than traditional methods, allowing astronomers to identify patterns and anomalies in celestial objects that would take humans much longer to discern. By sifting through countless images and spectroscopic data, AI can help pinpoint interesting targets for further study, such as exoplanets or supernovae, which might otherwise be overlooked. Moreover, AI can optimize the design of telescopes and sensors, using simulations to predict how changes in shape or material could improve performance, thus guiding engineers in creating more sensitive and precise instruments. In addition, AI can enhance the calibration process of these instruments, ensuring they remain accurate over time. By using real-time data analysis, AI algorithms can adjust the settings of telescopes automatically, compensating for atmospheric disturbances or mechanical drift, thus maintaining the quality of the observations. This capability is particularly beneficial for large observatories that operate multiple telescopes simultaneously, as it reduces the manual workload for astronomers and technicians. Furthermore, AI can facilitate the development of adaptive optic systems, which are used to correct distortions caused by the Earth's atmosphere. By predicting atmospheric turbulence in real time, AI can adjust the shape of a telescope's mirror to counteract these effects, allowing for clearer and sharper images of distant galaxies, nebulae, and other celestial phenomena. This technology has already led to significant advancements in ground-based astronomy, enabling scientists to explore the universe in greater detail than ever before. On the software side, AI improves data management and sharing among astronomical research institutions. Big data analytics, powered by AI, helps in organizing the massive amounts of information generated by surveys and observational campaigns. By categorizing this data efficiently, AI can make it more accessible for researchers worldwide, fostering collaboration, accelerating discoveries. AI also plays a crucial role in the development of new types of detectors, which are essential for capturing the faint light from distant objects. By analyzing how different materials respond to light and other wavelengths, AI can suggest new combinations or structures that enhance sensitivity and efficiency, leading to the creation of next-generation sensors that can detect previously invisible phenomena. Moreover, AI-driven simulations of cosmic events, like supernova explosions or galaxy formations, provide valuable insights that inform the design of new instruments. These simulations can predict how these events would look under various observational. As we look ahead, the intersection of artificial intelligence and astronomy is poised to bring about transformative advancements, shaping the future of our understanding of the universe. One of the most promising trends is the development of machine learning algorithms, which are becoming increasingly sophisticated in analyzing vast amounts of astronomical data. Large telescopes, such as the Vera C. Rubin Observatory, will generate petabytes of data, and AI will be essential in sifting through this information, identifying patterns, and making sense of complex phenomena, such as the behavior of distant galaxies or the characteristics of exoplanets. Moreover, AI's ability to recognize anomalies in data could lead to the discovery of new celestial objects, enhancing our knowledge of the cosmos in ways we can hardly imagine. Additionally, natural language processing, a branch of AI that deals with human language, will likely play a role in improving how astronomers communicate their findings. Researchers will be able to use AI to generate reports or even summarize complex research papers, making the information more accessible to both scientists and the general public. This democratization of knowledge could foster greater public interest and involvement in astronomy, as people can more easily understand and engage with the latest discoveries. Furthermore, AI is expected to enhance simulations of cosmic events, allowing astronomers to create more accurate models of phenomena such as black hole mergers or supernova explosions. By training models on existing observational data, AI can help predict future events or outcomes, offering insights that were previously unattainable. These simulations could also assist in planning future missions, guiding telescopes to observe the most promising targets based on predictive analytics. In the realm of robotics, AI-driven autonomous telescopes and drones may revolutionize the way we explore space. These systems could operate without human intervention, conducting surveys of the night sky and gathering data on various celestial bodies, potentially covering areas of space that have not yet been thoroughly examined. This capability would not only increase the efficiency of astronomical research, but also reduce the costs associated with space exploration missions. Moreover, the integration of AI in data reduction processes will streamline the analysis of signals from radio telescopes, helping to identify potential extraterrestrial communications. Projects like the Search for Extraterrestrial Intelligence SETI are already benefiting from AI technologies that can analyze signals more effectively, filtering out noise and focusing on genuine signals that may indicate intelligent life beyond Earth. As we venture further into the cosmos, the collaboration between astronomers and AI specialists will likely deepen, leading to innovative tools and methodologies that will redefine our approach to exploring artificial intelligence, or AI, has become a powerful tool in the interpretation of data from multi-wavelength observations, which are crucial in understanding the vast array of phenomena occurring in our universe. When scientists collect data across different wavelengths, from radio waves to visible light, and even to gamma rays, they encounter an immense amount of information that can be difficult to analyze and interpret. AI can streamline this process in several remarkable ways. One of the primary methods is through machine learning algorithms, which can be trained to recognize patterns within large data sets. For example, AI can help identify celestial objects, such as stars, galaxies, and black holes, by analyzing light curves and spectral data, enabling researchers to classify these objects more accurately and efficiently than traditional methods would allow. Moreover, AI can assist in the extraction of meaningful insights from the complex data generated by various observational instruments. By using deep learning techniques, AI can analyze images taken by telescopes across different wavelengths, revealing features that may not be easily discernible to human eyes. This capability is particularly valuable in astrophysics, where the sheer volume of data can overwhelm even the most experienced scientists. Additionally, AI can enhance the capabilities of simulations and models, allowing researchers to predict how astronomical phenomena evolve over time, based on the data gathered from multi-wavelength observations. This predictive power can lead to new discoveries about the life cycle of stars, the formation of galaxies, and even the behavior of dark matter. Furthermore, AI can facilitate the integration of data from multiple sources, harmonizing observations from different telescopes and instruments. For instance, when data from X-ray observatories is combined with infrared observations, AI can help synthesize this information to create a more comprehensive picture of cosmic events. This holistic approach is crucial in fields like astrophysics and cosmology, where understanding the interplay between different wavelengths can reveal the underlying physics of the universe. One of the exciting developments is the use of AI in identifying transient events, such as supernovae or gamma ray bursts, which occur over very short timescales. Traditional observation methods might miss these fleeting phenomena, but AI algorithms can sift through continuous streams of data, flagging anomalies that warrant further investigation. This capability not only enhances our understanding of these spectacular events, but also aids in planning follow-up observations with other telescopes. Moreover, AI can also play a crucial role in automating the process of data analysis, reducing the time scientists spend on manual data interpretation. By automating routine tasks, researchers can focus their efforts on more complex. Astronomers, who delve into the vast and mysterious universe, require a unique set of skills to effectively utilize artificial intelligence in their research, blending the realms of science and technology in remarkable ways. First, a strong foundation in mathematics is crucial, as astronomers often use complex algorithms to analyze vast amounts of data collected from telescopes and space missions. This mathematical proficiency enables them to create models that can predict celestial events, analyze cosmic phenomena, and interpret data patterns, which are essential for understanding the universe's workings. Moreover, programming skills are increasingly important, allowing astronomers to write and modify code that drives AI systems. Familiarity with programming languages such as Python or R is beneficial, as these languages are widely used for data analysis and machine learning applications. Understanding how to implement machine learning techniques such as neural networks can help them improve the accuracy of their analyses, enabling them to sift through enormous data sets to find meaningful insights that would otherwise be missed. In addition to technical skills, critical thinking is vital, as astronomers must assess the reliability of the data generated by AI algorithms. They need to question the outcomes and ensure that the models they use are valid and applicable to their specific research questions. This analytical mindset helps them discern between noise and significant signals in the data, ensuring that their findings contribute to the broader understanding of astrophysics. Collaboration skills are also key, as many astronomical projects are interdisciplinary, involving teams of scientists from various fields, including computer science, engineering, and physics. Effective communication becomes essential, as astronomers must convey complex ideas clearly and work together with others who may have different expertise. This collaborative spirit fosters innovation, leading to new ways of using AI to explore the universe's mysteries. Furthermore, an understanding of data science principles is increasingly important in the field of astronomy. As AI techniques become more prevalent, astronomers need to be familiar with data preprocessing, feature selection, and model evaluation, ensuring that the data they feed into AI systems is suitable for analysis. This knowledge allows them to enhance the quality of their research and leverage AI technologies to uncover new astronomical phenomena. Lastly, a curiosity-driven mindset is indispensable for astronomers using AI. The desire to explore and discover pushes them to ask innovative questions and pursue new avenues in their research, encouraging the development of novel AI applications that can push the boundaries of what we know about the universe. By combining these skills, astronomers are well equipped to harness the power of artificial intelligence, unlocking new insights into the cosmos. In the next decade, the role of artificial intelligence in astronomy is expected to evolve in profound and exciting ways, as astronomers increasingly turn to advanced algorithms and machine learning techniques to analyze vast quantities of data generated by telescopes and space missions. The growth of large astronomical surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, will produce petabytes of data, making it nearly impossible for human researchers alone to sift through and interpret all this information. So AI will be crucial in automatically identifying celestial objects, classifying them, and even predicting their behaviors. For instance, AI systems are being developed to detect transient events like supernovae or gamma-ray bursts much faster than traditional methods, allowing astronomers to respond to these fleeting phenomena in real time, leading to more discoveries and deeper insights into the universe's dynamics. Furthermore, machine learning techniques are being applied to analyze the cosmic microwave background radiation, helping scientists understand the early universe and the fundamental physics that govern it. thus providing a clearer picture of cosmic evolution. Additionally, AI is expected to assist in exoplanet detection, where algorithms can analyze the light curves of stars to spot the telltale signs of planets passing in front of them, a method known as the transit method, which has already led to the discovery of thousands of exoplanets. But with AI, the search can become even more efficient, identifying Earth-like planets in habitable zones around stars more quickly. The integration of AI in simulating astrophysical phenomena is another area where advancements will be significant. Complex simulations of galaxy formation or black hole mergers require immense computational power, and AI can optimize these processes, making them more efficient and accessible for researchers. Moreover, AI's role in data-driven astronomy will foster collaboration across disciplines. As techniques develop for other fields, such as image recognition and computer vision or natural language processing, can be adapted to analyze astronomical data, leading to cross-pollination of ideas and methods that will enhance our understanding of the cosmos. As AI becomes more integrated into the scientific workflow, we can expect a shift in how scientific discoveries are made, with AI not just serving as a tool, but also contributing to hypothesis generation and the formulation of new theories which could revolutionize the way astronomy is conducted. In addition, ethical considerations surrounding the use of AI in astronomy will also evolve, as astronomers will need to address issues related to bias in data training sets and the transparency of AI algorithms, ensuring that astronomical data interpretation, a fascinating field, is increasingly being revolutionized by artificial intelligence, with AI systems now capable of analyzing vast amounts of data collected from telescopes, satellites, and various space missions, allowing scientists to uncover patterns and insights that would be nearly impossible for humans to discern alone. For instance, machine learning algorithms can detect exoplanets by analyzing light curves from distant stars, identifying tiny dips in brightness that suggest a planet is passing in front of the star, which has led to the discovery of thousands of exoplanets, some of which may have conditions suitable for life. Furthermore, AI assists in classifying galaxies, distinguishing between different types based on their shapes and sizes, which helps researchers understand galaxy formation and evolution, thereby providing a clearer picture of the universe's history. Another important aspect is the ability of AI to process and analyze data from gravitational wave detections, where algorithms are trained to recognize the unique signatures of these cosmic events, enabling scientists to explore phenomena such as black hole mergers and neutron star collisions, which were once beyond the reach of human analysis. Moreover, the use of AI in analyzing cosmic microwave background radiation has given rise to new insights about the early universe, as these algorithms can sift through the noise to identify subtle fluctuations that reveal information about the universe's age and expansion rate. As we look to the future, the implications of AI in astronomy are profound, with ongoing advancements suggesting that we may soon have autonomous telescopes equipped with AI to conduct observations and make decisions in real time, optimizing data collection based on immediate findings, which could lead to groundbreaking discoveries. Additionally, AI has the potential to enhance our understanding of dark matter and dark energy, as researchers develop models to simulate the universe's behavior under various conditions, helping to explain phenomena that remain elusive to current scientific understanding. The collaborative efforts between AI researchers and astronomers are paving the way for new tools and techniques, fostering an environment where interdisciplinary approaches can thrive. And this synergy is not only enhancing our comprehension of the cosmos, but also pushing the boundaries of what we consider possible in scientific inquiry. As AI continues to evolve, its role in managing and interpreting astronomical data will likely expand, opening doors to new realms of exploration and understanding, and inspiring future generations of scientists to delve deeper into the mysteries of the universe.